This will be the 7th grade notes for Unit 6-3, theoretical and experimental probability. So most of pretty much everything that we've talked about so far has been theoretical probability. When we talk about trying to roll a die, and probability of getting a 1 would be 1 out of 6. That's what should happen, what we think in theory should happen. Occasionally we've talked about experimental. If I tried rolling that die and I wanted to get a 1, well, I could roll it 6 times and I should get a 1, but if I do the actual experiment, I could get a 1 every single time. I might never get a 1. So experiment is what actually happens. So theoretical is what we think should happen. Experimental is what actually happens. And like I said, we've talked about a little bit of this already, so we're going to go and dive right on into this. So example 1 says the graph shows the results of an experiment in which a number cube was rolled 100 times. Determine the experimental probability of rolling a 3 for this experiment, then compare it to the theoretical probability. Well, I know it says number cube, but we're just talking about rolling a die or a dice or however you want to phrase it. So I'm going to go ahead and talk about the theoretical probability for this part. So in theory, if I wanted to roll, I already forgot what we're supposed to roll. We want to roll a 3. Well, in theory, there's only one 3 on a die. Well, there are a total of 6 options. So my theoretical probability is 1 in 6 of rolling a 3. But whoever is doing this experiment has already rolled 100 times. So I'm going to go over here and I'm going to look at their actual experiment. Well, here's the 3 that they rolled. And if I look at the chart, they rolled it 16 times. So what they wanted is a 3, and they rolled it 16 times. And I'm still doing it just like I did before. I'm doing my want over my possible. So we wanted a 16. Well, in the possible rolls, well, they did a total number of 100 rolls. So 16 out of 100 is perfectly fine, but I would like to simplify this. Both of those are even, so I'm going to cut them both in half. Well, both of those are also even, so I'm going to continue to cut them in half. And then we get 4 out of 25. So out of 25 rolls, for their experiment, we would have expected them to roll a 3 4 times. So this is our experimental probability. I'm going to do that one in blue just to separate it. Okay? Let me finish reading through this example real quick. So it says the experimental probability of rolling a 3 is, well, we just came up with that, 4 out of 25, because that's what actually happened, which is close to the theoretical probability of 1/6. Well, I know it's really difficult to tell whether that's close or not. So I'm going to change both of these to decimals real quick. So what I'm going to do is I'm going to cheat and I'm going to use my phone. I'm going to do 4 divided by 25. Well, that comes out to 0.16. Now over here, I'm going to change this to red just because we're talking about theoretical now. I'm going to do 1 divided by 6. Well, that comes out to 0.16 repeating. So you can see that those two are actually really dang close to each other. And that's what we would expect most of the time. We would expect our theoretical probability and our experimental probability to be really close. Doesn't have to be, but that's what we expect to happen. On to example 2. In a telephone poll, 225 people were asked whom they plan to vote for in the race for mayor. What is the experimental probability of Juarez getting a vote from a person selected at random? So let's talk about the experimental. They have, let's see, how many people did they call? They called 225. So I know my denominator is going to be 225 because that was the total number of people called. Juarez was called 75 people that were called said they'd vote for Juarez. So it's 75 out of 225. I'm going to go ahead and simplify this. 25 goes into 75 3 times. 25 goes into 225 9 times. And both of those can still be simplified. 3 goes into 3 once. 3 goes into 9 3 times. So our experimental probability is 1 in 3. So it says of the 225 people polled, 75 plan to vote for Juarez. So the experimental probability is 1 in 3. On to example 3. Suppose 5,700 people voted in the election. How many can be expected to vote for Juarez? Okay, so this comes down to a proportion. This is now our ratio. I know it's our experimental probability, but we're going to use it like a ratio. What we're going to do is we're going to set up a line equals line or a proportion or whatever you want to call it. And we want to see for a total of 5,700 people voting. Well, that's our total number of people, so that will go down here. And we want to find out how many of those people are going to vote for Juarez. From here, it's just a matter of doing cross multiply divided by the lonely guy. So here, well, 1 times 5,700 is still going to be 5,700. So now I've got to do 5,700 divided by 3. I'm dividing by my lonely number. When I divide those two, I get 1,900. Now, for our experiment, we would expect, this is why they do these kind of polls. They call around, they try to figure out who people are going to vote for. And so with their experiment that they did, they would expect 1,900 people to vote for this person. Do we know for sure that that's what's going to happen? No, but statistically, with the people that we surveyed, we would expect this to happen. Doesn't necessarily have to work that way. Ask me about how actual polls and voting and elections have gone sometime. All right, for this exercise portion, for exercise 1, it says, use the graph of a survey of 150 students asked whether they prefer cats or dogs. What is the experimental probability of a student preferring dogs? Okay, so first we need to know how many students. Well, we already said that there are 150 students that were surveyed for this thing. And looks like we have dogs and cats cut off. I'm not sure why it's cut off, but I'm pretty sure we all know that everybody loves dogs more than cats. So I'm just going to label it like that. Anyway, so for our experimental probability of students preferring dogs, we're going to say that it was that 132 that voted for dogs out of the 150. Now we just got to simplify it from here. Both of these are even, so I'm going to cut both of those in half. Both of those are divisible by 3. And I think that's about as simplified as that's going to get. So if we'd actually only surveyed 25 people, we'd expect 22 people to like dogs more than cats. Or, pretty much all of them, because dogs are better than cats. Part B. Suppose 100 students were surveyed. How many can be expected to prefer dogs? Okay, so we've got our ratio right here that we just came up with, our 22 out of 25. They want to know, let's say we surveyed 100 students instead of 150. I'm going to take that 100 and I'm going to put it down here because I want to know how many would vote for dogs out of that 100. Here, usually we can do cross multiply, divide by the lonely guy, but I see a nice easy way to scale this. To go from 25 to 100, I can do times 4. So I'm going to do the same thing here. I'm going to do times 4. When I multiply those two, I get 88. So I know that if I've surveyed 100 people, I would expect 88 of them to prefer dogs. Part C. So suppose 300 students were surveyed. How many can it be expected to prefer cats? Well, probably none of them because cats suck. But we're going to play along and we're going to pretend like some people like cats. So 18 out of 150. So 18 out of 150 is what actually happened. Now, we're going to do this with 300 students instead. So I'm going to put that 300 down here because I want to know how many would vote for cats. None. Again, I see a nice easy way to scale this. So what I'm going to do is I can multiply this times 2. So I'm going to do the same thing right here. I'm going to do times 2 instead. If you don't like that method, you can absolutely do cross multiply divide, but this will save you some time. So I would expect 36 people to vote for cats out of 300. If we had surveyed 300 people, 36 would say they like cats. All right, on to the back side. The table shows the results for a fair number cube rolled 40 times. So I know that my total here is going to add up to 40 because that was a total of 40 rolls. So number 1 says determine the experimental probability of rolling a 4. Well, that 4 was rolled 8 times out of 40. Now I just need to simplify. Both of those are divisible by 2, so I'm going to cut them both in half. Both of those are also divisible by 2. I'm going to cut them in half. Still divisible by 2. Going to keep cutting them in half. So I have a 1 in 5 chance experimentally of rolling a 4. But now the theoretical probability of not rolling a 4, I'll be honest, I don't really like that. I want to change this to rolling a 4 because I want to compare them. So we're going to do this for actually rolling a 4. Well, there's only one 4 on a number cube or on a die out of 6 total options. So you can see that 1/5 and 1/6, those two are going to be pretty darn close to each other. If I wanted to do the not part, Well, of not rolling a 4, well, there are 5 numbers that are not a 4. So the not part would be 5 out of 6 if you did it that way. But like I said, that doesn't make any sense for 1 and 2. I want them to look similar to each other. All right, number 3 says determine the theoretical probability of rolling a 2. So in theory, what should happen? Well, there's only one number 2 out of 6 total options. So that is my theoretical probability of rolling a 2. Number 4, determine the experimental probability of not rolling a 6. Okay, we rolled a 6 4 times. For whoever's not seeing that part. If we rolled a 6 4 times out of a total of 40 rolls, well, that means that we did not roll 6. Like these right here, that's 36 rolls. So for not rolling a 6, we didn't roll a 6 36 times out of 40 total rolls. And again, I can simplify both of these. So 36 divided by 2 is 18. 40 divided by 2 is 20. Both of those are still even. So I get 9 over 10. So I have a 9 in 10 chance of not rolling a 6. Final one. Number 5 says, suppose the number cube is rolled 500 times. Based on the results in the table, about how many times would it land on 5? So we're doing the experiment now. I know my color's getting jumbled up here. Here's my 5. We rolled it 12 times. So 12 out of my 40 rolls. And we want to know for 500 times. If we rolled that thing 500 times, how many times would we expect to land on that 5? Now, looking at this, there's not exactly a nice way to scale this. So I think what I'm going to do is I'm going to try to simplify this part first. I think that'll make my life a little bit easier. So I'm going to make this 6 over 20. I just cut both of those in half because I know 20 can go into that 500 nicely. So I'm still doing the same problem. I just wanted to simplify it first. So 20 can go into, let me change colors here real quick. 20 can go into 500 25 times. So I can multiply that by 25. So I'm going to do the same thing here, times 25. Well, 6 times 25 is going to be 150. So if we did that experiment 500 times, we would expect to land on 5 150 times. All right, this is the homework section. For the most part, you guys are on your own, but I'm going to do a few of these anyways. So a number cube is rolled 50 times, and the results are shown in the graph to the right. So this is a total of 50 times over here. Number 1, determine the experimental probability of rolling a 2. Well, we rolled a 2 8 times, so I would make that 8 out of 50. Again, need to simplify both of these, so I would make that 4 over 25. But now let's know what the what is the theoretical probability of rolling a 2? Well, on a cube, on a die, whatever else, there's only one number 2 out of a total of 6 options, so 1 and 6. Number 3, determine the experimental probability of not rolling a 2. Okay, so first, I need to know how many not 2s are there. Well, we rolled that 2 8 times. So remember, that's right here. We rolled it 8 times. If I do 50 minus 8, I know that these other times, like if I add all the blue ones that I'm circling, that should be a total of 42 times that we did not roll a 2 out of a total of 50 rolls. And again, I can simplify that. Both of those are even, so that makes that 21 over 25. Number 4, what is the theoretical probability of not rolling a 2? Well, on a number cube or on a die, there are 5 sides that are not a 2 out of a total of 6 sides. And number 5, determine the experimental probability of rolling a 1. Okay, so now I'm going to change colors up on you. Here's the 1. We rolled a 1 10 times. And then we rolled a total of 50 rolls. Well, that simplifies really nicely down to 1/5, which is pretty darn close to 1/6. All right, now down for this part. All right. Use the results of the survey at the right. So number 6, what is the experimental probability that a person's favorite season is fall? Write the probability as a fraction. Okay, I'm only going to do one of these for you. I want you to do the rest on your own. But there's fall. It's 25%. Well, because it's a percent, I can make that 25 out of 100. So all of these, I would talk about these out of 100. So 25 goes into 25 once, 25 goes into 100 4 times. That is our probability of somebody liking fall. Actually, I said I was only going to do that, but I'm going to do one more. Out of 300 people, how many would you expect to say fall is their favorite season? So we've got our 1 out of 4. I'm actually going to use the 25 out of 100 on this just because it goes into 300 nicely. And I want to know if we had 300 people vote. Well, again, I could do cross multiply divide, but I can see that I can just multiply this times 3. So I can do this times 3. So I would expect 75 people out of 300 surveyed to like fall. You guys are on your own for the last two.